In this video, we are going to look at ultraviolet visible spectroscopy, or as it's also called, UV Vis Spectroscopy. Ultraviolet visible spectroscopy, or sometimes for short we call it only ultraviolet spectroscopy, even though we record spectrum both in ultraviolet and visible part of the electromagnetic spectrum, is a spectroscopic method that is based on interaction of molecules, ions, atoms with ultraviolet and visible parts of the electromagnetic spectrum. Instrument that is used in this type of spectroscopy is relatively simple. It contains energy source, and that energy source is typically a tungsten lamp which serves as source of visible light, and deuterium lamp that is source of ultraviolet radiation or ultraviolet light. So both lamps are actually turned on, and light from or radiation from both sources passes through the sample, and that sample is in a cuvette. There are different sizes cuvettes, but usually we use 1 centimeter long cuvette. Next, the radiation passes through a narrow slit, and finally it hits a dispersion device. That dispersion device in the past used to be a prism. Now it's more likely a diffraction grating. And in fact, this instrument is so simple that often homemade instruments are used in simple lab exercises. And those instruments can be used by using either a CD or DVD as diffraction grating. And finally, there is a detector. These days, detector is a CCD, charged coupled device, which is similar to what we have in electronic cameras. Here we have an expression for energy of ultraviolet radiation, which I presume you are already familiar with. And so energy of UV radiation, ultraviolet radiation, is sufficient to promote an electron from ground state to an excited state. So UV visible spectroscopy promotes electronic transitions. And spectrum is a plot of intensity of absorbance as a function of wavelength. Typically, UV visible spectrometer, if it's of good quality, records in range of between 200 and 800 nanometers. UV absorption bands, as you can see from this example of the spectrum, are very broad. And that's because, in addition to simple electronic transitions between different electronic levels, there are overlapping vibrational and rotational energy sublevels, and they result in broadening of absorption bands. Each band has its maximum, absorption maximum, and so each band is characterized by absorption maximum or lambda max. And that's what we report as ultraviolet spectrum of a compound. Ultraviolet visible spectroscopy has relatively low information content compared to other spectroscopic methods. Also, not all compounds are active in this type of spectroscopy. Not all compounds absorb ultraviolet and visible radiation. This method is limited typically to unsaturated compounds, and also the actual spectrum depends on the solvent and may change from one solvent to another. So this type of spectroscopy has rather limited application. Energies involved in ultraviolet visible spectroscopy are sufficient to promote an electron from one of the filled orbitals to one of the empty orbitals. And we describe type of electronic transition by considering orbitals that are involved. So the lowest energy transition would involve n to pi star electronic transition. That's transition from non-bonding orbital, that means orbital where free electron pairs are present. So from non-bonding orbital to antibonding pi orbital. Of course, energy of electromagnetic radiation is proportional to its frequency and inversely proportional to its wavelength. In this case, in case of ultraviolet visible spectroscopy, we use wavelength as a scale. So since energy is inversely proportional to wavelength, short wavelengths mean high energy and long wavelengths low energy. So n to pi star transition will be long wavelength transition. it will certainly have longer wavelengths compared to other transitions that we are about to cover. Next, in the order of increasing energy, is pi to pi star. So, electronic transition from bonding pi orbital to an anti-bonding pi orbital. And since it has a bit higher energy compared to n to pi star transition, then lambda max is a little bit shorter number, a little bit smaller number, indicating higher energy. Then next in the order of increasing energy is n to sigma star transition. That's transition from non-bonding orbital to sigma anti-bonding orbital. And again, wavelength gets progressively shorter as energy required for electronic transition increases. As we go further in the order of increasing energies, next one is pi to sigma star. That means electronic transition from bonding pi orbital to an anti-bonding sigma orbital. Again, lambda max gets even shorter compared to previous ones. And finally, the highest energy transition that can be observed by ultraviolet spectroscopy is sigma to sigma star. So electronic transition from bonding sigma orbital to an anti-bonding sigma orbital, and those are shortest energy transitions. Typically they are in far UV, and usually they cannot be observed by ordinary UV instruments. We need some special instruments that can absorb, that can do so-called vacuum UV spectroscopy. But there are exceptions, and one of those exceptions are carbon-iodine bonds. So carbon-iodine bonds can be observed by UV visible spectroscopy. Compounds that are most commonly studied by UV visible spectroscopy are unsaturated organic molecules. In unsaturated compounds, the degree of separation among non-bonding, bonding, and anti-bonding orbitals depends on the presence of free electrons, if any, number of double bonds in conjugation, and on the nature of the substituents on the double bonds. So here we have an example of simplest double bond, molecule of ethene. So there are no free electrons, there is only one single double bond, and there are no substituents. The energy for pi star transition is actually very high, and lambda max is 171 nanometers. That's actually below 200 nanometers cutoff that we can observe under ordinary UV visible spectrometers that use quartz cuvettes, because quartz absorbs below 200 nanometers. So we have to, for something like this, we have to use vacuum UV. So this is typically a compound that would not be suitable. So just one double bond without any substituents, without any free electron pairs. That's actually not a compound that will be suitable for study by UV visible spectroscopy. Here we have an example of molecule of acetone. So here, in addition to double bond, so pi to pi star transition, we also have free electron pairs on oxygen. So we have presence of free electrons. Free electron pairs on oxygen atom enable n to pi star transition. That's much lower energy transition, and since we have n to pi star transition, then lambda max for this transition is 279 nanometers. So that shows how much lower energy is needed for this electronic transition, and this is obviously something that we can easily observe and study by UV visible spectroscopy. Here is an example how conjugate double bonds affect energy required for pi to pi star transition. So first example, as standard, as a benchmark, is what we have already seen, pi to pi star transition in molecule of ethene. So we have already seen that very high energy is required for that transition, and so lambda max is 171 nanometers, not suitable for study by UV spectroscopy. But when we look at next example, now we have two conjugated double bonds, molecule of 1,3-butadiene. And previously, in previous chapters, we have covered energy levels of the localized compounds of conjugated dienes and polyenes like this. So you know that energy levels stack up. And so you can see that electronic transition from HOMO, highest occupied molecular orbital, to LUMO, lowest unoccupied molecular orbital, now requires considerably lower energy. And so lambda max for 1,3-butadiene is 270 nanometers, as energy HOMO-LUMO gap energy has narrowed. And the more conjugated double bonds there are, the smaller the HOMO-LUMO energy gap is. The smaller the gap between the highest occupied and lowest unoccupied molecular orbital. So in 135 hexatriene, lambda max is only 263 nanometers. And you can tell from this how quickly energy gap is narrowing. By the time there are about 7 double bonds in conjugation, compound starts to absorb invisible part of the spectrum, and then that means the compound is colored. So as you can see, UV visible spectroscopy is a useful method for study of conjugated dienes and polyenes, and it could give us some idea about the number and nature of those conjugated double bonds. Unsaturated carbonyl compounds that have conjugated double bonds, as in this case, this would be methylvinyl ketone, its real name. We often observe more than one absorption band, and so in this case we observe lambda max at 210 and 315 nanometers. So 210 would be pi to pi star transition, so transition from bonding to antibonding pi orbital, and 315 n to pi star. So non-bonding electrons, free electrons from oxygen, non-bonding electrons to antibonding pi orbital. This completes our study of ultraviolet spectroscopy, and next we are going to look at infrared or IR spectroscopy.